All right, y'all. So I'm going to go ahead and solve a couple of these example problems. This is from our MA 4.8.2. These ones are from slide 8, and these ones are from slide 9. And so we're just solving trig equations, right? So I already solved the first one actually in class, so I'm going to do it pretty quick. But basically, guys, if you have cosine theta equals negative 0.4, we're going to need to use inverse cosine in order to get that solution. When I do inverse cosine, you just need to plug it into a calculator. I like to use Desmos. So I'm going to go ahead and plug that into Desmos real quick right now. Cosine to the power of -1 of negative 0.4. And so I get that theta is equal to 1.98. So then, guys, what we do here is we recognize that actually theta equaling 1.98 is not going to be the only solution where cosine is equal to negative 0.4, because remember, cosine is the x-coordinate, right? Here's negative 0.4. And so here's 1.98. By the way, this is radian, right? So I have 0 radian, I have pi over 2 radian, I have pi, I have 3 pi over 2, and I have 2 pi. These are like kind of the quadrants. It's useful to keep these in mind because it helps us know kind of our boundaries. We said that cosine was the x-coordinate. So where else do I have an x-coordinate of negative 0.4? You can see down here I have it, right? How do I find this guy? Well, here's 1.98. I can see that the angle to get to 1.98 is the same as if I go backward from 2 pi to here. So what I'm going to do is to find this, I'm going to do 2 pi minus 1.98, right? 2 pi is actually 6.28. So if I do this subtraction, I get 4.3. So 4.3 is going to be the second solution. Now, there's a thing though. My domain is all real numbers. So I need to account for that by using a general solution. So I'm not going to just have 1.98 and 4.3, because if you guys think about it, right? Watch this, I'll do it in a different color. If I went one full loop, which is 2 pi, and then I added the 1.98, I'm in the same exact location, which means that I have the same x-coordinate. So therefore, it's also a solution. So I need to account for all these, the fact that I can just do any amount of loops around the unit circle. So what I'm going to do is I'm going to say my solution is actually theta is 1.98 plus a full loop in the context of just cosine. The period is 2 pi. So I can add 2 pi and I can add any number of 2 pi's. So that's why I use k, because k, I'm claiming that k is in integers. So k is an integer. So basically what that means, integers, remember integers are numbers like 1, 2, 3, 4, or -1, -2, -3, because I could actually also go backward a loop, right? So this is accounting for the fact that any number of loops around the unit circle, if I end up back at 1.98, right? So if I have a coterminal angle to 1.98, then it's also a solution. And then I also have 4.3 plus 2 pi k, because those would also all be solutions. And that's how I solved the first one. Let's do the second one then. For the second one, I have sine of t equals 0.58. Same thing, I just need to do an inverse sine. So I'm going to have t equals the inverse sine of 0.58. Let me just do that real quick on Desmos. Sine to the power of -1 of 0.58. I get that t would equal 0.62. Now, once again, we need to find the second solution using a diagram of the unit circle. So I'm going to do that real quick. I draw my unit circle. I know that I'm dealing with sine, which is the y-coordinate, right? Sine is the y-coordinate. So I know that I'm looking for y-coordinates that are 0.58. Well, I have one here, and I have one here. Which of these do you think is the 0.62? We've got 0, we've got pi over 2, we've got pi, 3 pi over 2, and we've got 2 pi back here. Pi over 2 would be equivalent to 1 point, let's see, 3.14 divided by 2 would be 5.7. So clearly this one here is 0.62 because I am before I hit pi over 2, right, which is 1.57. What I can observe is that the angle here to get to 0.62 is the same as the angle for the second solution away from pi. So I'm just going to take pi, right, 3.14, and subtract 0.62. So let's see what we get when we do this. I would get 2.52. So t is equal to 0.62 and also 2.52. Now, let's deal with the fact that there could be more than these two solutions, right? Because if I do loops, right, if I do another loop and I end up back at 0.62 with a coterminal angle, then I would also have the same solution. Now, what's important to look at, guys, is your domain. I have a domain from 0 to 4 pi, so it's not going to be the general solution like number 1 was, but I could have 0.62 plus 2 pi, right? 0.62 plus 2 pi. I could also have 2.52 plus 2 pi. I cannot have 0.62 plus 4 pi, right? I can't have this because this would be greater than my domain, which is 4 pi. This is greater than, so this cannot be a solution. So my only solutions are going to be 0.62, 2.52, 0.62 plus 2 pi, and 2.52 plus 2 pi. And that's number 2. Now let's look at the ones from slide 9. These ones are a tad bit more complicated just because there's like some more algebra to be done, but they're not that crazy, right? Check it out. If I have 2 sine of theta plus 3 equals 0, I can subtract 3 from both sides, and I get 2 sine of theta equals -3, and then I divide both sides by 2. And as I'm doing this, I'm now realizing that Mr. Hobaugh made yet another mistake on these slides. That guy. How dare he? Because there's a problem here, guys. Sine cannot be... If you look at the sine function, it goes up and down around 1 and -1. So can sine be equal to -3/2? It can't. So actually what would happen here, guys, is technically, let's solve this anyways. What's the solution? There are no solutions, essentially, right? So essentially what we would say is just no solutions. You know, this is actually a fair exercise to see. So we recognize that there's no solutions to this equation, and that's our answer, actually. You know what? This was a happy mistake because at least it let us talk about what happens when there can't be a solution. You just have to say there are no solutions. And that's actually a perfectly viable answer when there are no solutions. So now let's do number 2. This one actually I did do correctly, or I did properly. So we're gonna try to solve this, and we're trying to solve for x, guys, right? What I want you to see is this. I cannot get to x until I can get rid of this cosine. I can't get rid of this cosine until I can isolate it, though. So what I'm going to do is I'm going to first add 7 to both sides. And I get 4 cosine of pi over 5 x equals -5 plus 7 is 2. Now I'm going to divide both sides by 4. And I get cosine of pi over 5x equals 1/2. And now I'm going to do the inverse cosine. So I get pi over 5x equals the inverse cosine of 1/2. Now, you could plug this into your calculator, but actually, if you look at the unit circle, cosine's able to equal 1/2. Look at the unit circle, and right, you'll notice that cosine equals 1/2 at 2 values. And this one here is at pi over 3. If you look at your unit circle, you would see that. And the one down here is 5 pi over 3. So what I end up seeing is that I get pi over 5x equals pi over 3, comma 5 pi over 3. Now, there's kind of two ways I can do this. I can proceed from here. I'm going to focus in on this problem here. There's two ways I can proceed. So I'm going to set myself up to solve it two different ways. The first way I could do it is I could just continue solving this as if it is algebra, right? So I need to get rid of the pi over 5, so I'm going to multiply by 5 over pi, right? Because those would cancel. I need to multiply both sides by that, right? So what do I get? Well, these guys cancel, and I'm left with x equals pi over 3 times 5 over pi, comma 5 pi over 3 times 5 over pi. That was 5 over pi. So I have x equals, the pi's would cancel out here. I get x equals 5 thirds, and I also get 25 thirds. And then now I'm going to look at my domain. Remember, my domain was all real numbers. So I need to do that general solution. Now be careful here, guys. I'm not going to use 2 pi, right? Why am I not going to use 2 pi? Because my period's not 2 pi. Look at the b value. The b value was pi over 5. So my period would be 2 pi divided by pi over 5, which is 10. So I should do x is 5 thirds plus 10k, or 25 thirds plus 10k. So that's one way you could solve it, by essentially getting your two x values and then looking at the domain and dealing with it, right? That's one way you can do it. The other way you could do it is, as soon as I did the inverse cosine over here, as soon as I did inverse cosine, I could start recognizing that, okay, but I'm dealing with all real numbers, so my solution should be, plus 2 pi k. And then I could multiply both sides by 5 over pi. The problem with doing it this way is that it's kind of a little bit more complicated, honestly, because now I have to multiply 5 over pi to both of these terms here. But you'll see that it actually will give you the same answer. So I have x equals pi over 3 times 5 over pi plus 2 pi k times 5 over pi. And so then these guys cancel, the pi's cancel here, and I'm left with 5 thirds plus 2k times 5, which is 10k. So you see it's actually the same answer. And then for the second one, I have 5 pi over 3 times 5 over pi plus 2 pi k times 5 over pi. And same thing happens. So I get 5, the pi's cancel, and I get 25 thirds plus 2 pi k times 5 over pi. The pi's will cancel each other, and I'm left with 10k. So you can see that actually I can do it either way, but personally I think that it's actually easier to find your two solutions, or your two solutions within the single period, and then look at the domain and recognize what your general solution would be. I personally think that would be easier because it's pretty simple to figure out what your period is based on the b value here. So those were my solutions to the problems from 4.8.2.